Y is completely independent of X, because it's a completely unique direction. I cannot describe Y in terms of X. It's a unique vector. There is no property of X in this unit vector. They are fully orthogonal. This is important. I think you've heard this before. But try to think of it again. Orthogonality means that there is no information in this vector that is contained in that vector. They are completely independent. They have completely unique information to disseminate. They are orthogonal. That's why their dot product is 0. Okay, does it make sense? Because now we're going to make it a little bit more difficult. Okay? By the way, this condition is called orthonormality, and we'll use that word again. Orthonormality means that this is the normality condition, this is the orthogonality condition. Together it's called orthonormal. So these unit vectors form the so-called orthonormal set. But now I'm going to generalize this idea. Generalize it. I'm going to say, I'm not going to call this z coordinate now z, I'm going to call it g of s. Why? I'm going to allow it not just to be a simple unit vector. I'm going to say it is something more general than that. It is actually a function of some sort of variable s. Okay? So it's more general. It's not a unit vector. It's actually kind of a function vector. I have 3 again, g, h, and f. They form my new coordinates, but these coordinates are kind of different kind of coordinates. They have more information in them because they also depend on s. See that? It's more general. This is a different kind of space. It's not Cartesian space. This is a more generalized space. Still, there's only 3 components, g, h, and f, but they now depend on something else, s. In this new space, I can again describe a function or a point, p, which are basically projections along those functions. Okay, so if, compare this to the previous slide, and let's say if I call x the projection along f, and y the projection along h, and z the projection along g, then I can describe any point in this new space in terms of those new coordinates. This is very similar. I just changed the nature of these vectors. These vectors are now more general. Okay? So, my statement is that these new vectors that depend on s also are a complete set. And they have very similar properties as the properties before. Namely, if I take this, f of s, and then take the product, this is again a kind of a dot product, with itself, then I get 1. Same. Alternatively, if I take this coordinate f of s and I multiply it dot product wise with h of s, I integrate over all possible values of s, I get 0. Okay, this is very similar to what we got for the unit vectors, but of course I have to do something else, which is an integration over all values of s. But together, they form, again, the condition of orthonormality. These 2 conditions are the conditions for orthonormality. So they form a kind of a new coordinate system. It's a very different one, but it has similar properties. Same basic properties that the Cartesian coordinate system has, these have also. But it's more general. Okay, now, the last step we're going to do is this. We're going to say, why stop at 3 coordinates? Why not an unlimited amount? Okay? Just let that go. 3 is great, but just let that go. Why can I not just have more? So I'm going to say, I'm going to have a coordinate system which is composed of f, n, where n labels the coordinate. N can be 3, in the case of our simple example, but n can be 1,000 or infinite, right? Just think of the f's in the same way. These are basically the coordinates that span some sort of a space, and the space becomes more abstract, of course. It's no longer a Cartesian coordinate system. It's a different kind of space. But you can still think of it as a coordinate, because it has these mathematical properties of a coordinate. So, like I said, there's a condition here. And the condition is the following. If I take one coordinate, label it n, and I multiply it with another coordinate, labeled by m, then this so-called overlap integral is delta nm. What does that mean? This delta nm is called the Kronecker delta, and it has this very simple property. Namely, if n equals m, then it's 1, and it's 0 otherwise. So if n is not equal to m, it's 0. So that simply means that this overlap integral of fn dot product fm is 0 unless the two labels are the same. So this is the same as on the previous slide, but now generalized to an unlimited number of coordinates. Still the same property. Okay, so if I take that, I can now describe a point in this space, this guy, P of S, which is a point in that space, as a projection along each of the coordinates. Okay, this is again the same as we have written it before. Projection along x, y, and z. But now I have an unlimited amount, so projection along first n, second n, third n, fourth n, fifth n, sixth n, and so forth. A, n are the values of the projections, and fn is the coordinate. Is that meaningful? Well, you will see, we'll use this quite a bit. This P of S is actually a function of S. So, this is a function that I can describe in terms of these functions. Eigenfunctions of something, of an operator. These are the eigenfunctions of an operator that form a complete set. If I know these, I can describe this function in terms of these. Okay, so this thing here is a very important result. We will be using it quite a bit. Okay, so here's the same. I don't call it P, I'm going to call it G. I don't know why, but I'm just going to switch to a different letter. Okay, so G, the function G is described by a certain coordinate system, which is basically a coordinate system formed by f of n, where f of n is a complete set of eigenfunctions. Eigenfunctions of a particular operator. But the fact that they form a complete set allows me to make this, to have this description of the function g. Okay, so let's go back to the example that we had. We had a simple example of an operator. Take the second order derivative. And we found, let's say we found all the functions that are eigenfunctions of that operator. They form a complete set, which means I can have any given function g described as that so-called superposition of eigenfunctions, linear sum of eigenfunctions. Then, if I take the operator and I'm operating on this function g, which is a general function, what happens? Okay, so what I'm doing, I'm going to just write it out. I say g can be described in terms of these f's. So I'm going to operate on this linear sum of f's. See that? Now this operation only operates on the f's, not on the coefficients cn, because the coefficients are the value of the projections, which are constants. So this operator only operates on the f part of the sum. Okay? So that's what it is. I get a sum, constant cn, and then this operator operates on this function fn. So I know the answer of that because this operator, operating on Fn is an eigenfunction. That was the example that we had. Fn is an eigenfunction of this operator, and the eigenvalues that come out is omega n. So what I'm getting is this. I now get Cn times omega n times Fn. The question here is this new function g also an eigenfunction of this operator? And in most general terms, the answer is not necessarily. Okay, so the conclusion here is, and we'll use a conclusion later on. I'll try to illustrate what it all means. But for now, keep in mind, a linear sum of eigenfunctions is not necessarily an eigenfunction of the operator itself. All right, now, here, this is the last part of today's lecture, and it's about this integral here. Again, think of these Fn's, there are functions out of a complete set. I'm going to multiply one with another one, and then I'm going to integrate over all relevant variables. The variables that we call S at the beginning, I'm now going to tell you that those variables typically are X, okay? Position. And if I integrate in a three-dimensional space, I say dv. dv means I integrate over all spatial coordinates. So what I'm having here is the overlap integral of one coordinate with another coordinate. There's also a little asterisk there. Who knows what that asterisk means? That is a complex conjugate. The complex conjugate of the function Fn. We'll say more about that later on. But we have to put it there just in case if those functions, Fn, happen to be complex functions. Okay, so this is the complete expression of the so-called overlap integral of functions from a complete set. You already saw that the answer is this. Namely, this integral equals 1 if n equals m and 0 otherwise. So even though this is a very abstract thing, the answer is very simple. It's 1 or 0. That's it. Okay, so it is 0 if n is not the same as m, and the integral is 1 if n equals m. So what does that mean? What does it say about these functions? Well, it says the same about these functions as I said about the Cartesian coordinate system. There is no information in the function Fn that is also contained in Fm if n and m are different numbers. So one coordinate and the other coordinate, they don't share information. They are orthogonal. So the functions in a complete set of eigenfunctions are orthogonal functions. And if the last equation holds, this overlap integral equals 1 when n is m, then they are also normalized. So they're forming an orthonormal set. Fn and Fm, when they're different coordinates, different functions, different eigenfunctions, carry unique information. The information in one function is not contained in the other function. They are orthogonal. Okay, so let's use an example here, because that was very abstract, folks, in case you didn't notice. Here is a function f of x that I say looks like this. Okay, just an example. E minus ax. Okay, x runs from 0 to infinity. And I'm going to do the following. I'm going to require that this holds. Okay, I want this function to be part of a set that is orthonormal, which means that this particular overlap integral needs to hold. If I multiply this function with itself and I integrate over all x, then I should be getting 1. That's my requirement. Okay? That's what I require. So let's do that. You can also write it in the following way. Okay, because the complex conjugate times the function itself, I can write as modulus signs with a square, right? Have you seen that before? If not, that's the definition. The modulus signs with the square means the function f times its complex conjugate. Is this a complex function or not? It's not, because it doesn't have this complex number I in it. Okay? So it is a so-called real function. It doesn't have an imaginary part. This is a real function. So if I calculate this integral now with this particular function, what do I get? Function times itself. Okay, that is the function. E minus ax times itself. That is the integrand. I can rewrite that, of course, as e to the power minus 2ax. Integrated from 0 to infinity over x. I can do that because I know what the primitive is of this function, which is the function itself, times 1 over 2a with a negative sign. Okay, so this is the primitive of that integrand. And then I have to, of course, put in the values from the starting point to the end point of the integration. And what I'm getting is this. I just write it out, the whole thing. Okay? This is how you, of course, evaluate the integral. And what I get at the end is this number, 1 over 2a. So that is the value of this integral. The value of that integral is this, 1 over 2a. 1 over 2a is not the same as 1. But I want that condition to hold. I want the overlap integral of the function with itself to be 1. The value that it gives me is 1 over 2a. So this is not the same. Is that a problem? No, it's not. Not necessarily so. Because what I can do, I can simply say, well, this function was just not properly defined. I'm going to redefine it. I'm going to say the same function, but now there's a constant in front of it. I call it n. This is called the normalization constant. And I'm just going to see what is this n? What does n need to be for this normalization condition to hold? Okay, so again, I'm going to do the same calculation. But this new function includes the n. So what I'm getting now is this integral. It's the same integral as before, but now in front of it there is an n squared. The n is of course squared because I'm squaring the function. Okay? So this integral must be 1. Good news is we just solved already the value of the actual integral. That was 1 over 2a. I can use that result and plug it in right here. So what I'm getting is n squared times the value of the integral, which was 1 over 2a. That must be 1. Okay, that's 1. And from that, of course, I can determine what n squared should be. N squared should be 2a, which means that n is plus or minus the square root of that number. So plus minus square root of 2a. Two options here. Which one do I choose? Doesn't really matter, but it's common to take just the positive one. And so therefore, if I write a function like this, square root of 2a times this previous function, this whole thing now is what I call a normalized function. This function is normalized because it has that property of the overlap integral being 1. Okay? So that is a normalized function. We'll use this property a lot in quantum mechanics. We want our functions to be normalized. We want wave functions, which turn out to be eigenfunctions of operators. We want them to be normalized, and this is a procedure I can use to make sure that they are. Because that's not automatically fulfilled, I have to do a little bit of work to make sure that they adhere to the properties of an orthonormal set. Okay. That was a lot of stuff, folks. All right? I'll see you on Friday.